Okay, so the very first screen is extremely important for the rest of the course. The steps outlined here, which I'm actually going to break up every example into these 8 steps, are really the order of I don't want to say order of operations, but the order of what you're supposed to be doing for curve sketching, as well as often for optimization. Some key terms such as critical numbers, inflection points, and points, vertical asymptotes, local extrema. All of this comes back into play when we start Module 4, and Module 4 is very short on optimization. The lesson will be short, but the practice, every day we'll be practicing a bit of optimization. We are really going to end curve sketching mostly with today, with the exception of one example on Wednesday. So these steps, Mr. Bullock and I do expect to see in your study notes, and I did mention for Module 3 and Module 4, we are going to be marking those study notes very carefully and making sure there's lots of content in there. You'll notice this chart from my lesson last week, and it is really a summary of everything we've learned so far with the original graph, first derivative and second derivative, and what we can draw from the equations in order to help us with our curve sketching, but it also is a direct reflection of the steps I just referred to before. Okay, so we're going to start off with a question, and we're really going to flesh out 2 very long and detailed examples today. So the first one, use the algorithm for curve sketching to analyze the key features of each of the following functions and sketch a graph of them. Mr. Bullock, I believe one of your students is entering. Okay, so we start off with this cubic function, x to the power of 3 plus 6x squared plus 9x. Step 1 is to make sure if there are any restrictions in the domain or asymptotes, both horizontal and vertical. Because this is not a rational function, step 1 is irrelevant, but we can state that there are no restrictions on the domain and no asymptotes. For step 2, we have to look at x and y-intercepts. You'll remember for x-intercepts, you take the equation of the original graph and you set it equal to 0. So x cubed plus 6x squared plus 9x is equal to 0. Now, often we'd have to resort to synthetic division or long division, what you have all learned by now in the MCV4U course. But because there's a common x, greatest common factor of x for every term in this equation, I can factor the x out, which then gives me a simple quadratic equation to work with. And the quadratic equation can be factored. It is a perfect square. So x squared plus 6x plus 9 does convert to x plus 3 squared. So that gives me x is equal to 2 x-intercepts, x is equal to 0, and x is equal to -3. Now remember, that's not enough. By plugging these 2 x values into my original graph, usually that's what I would do with critical numbers, but because I know these are x-intercepts, I know that the y value is 0 in each case. So we're not looking for critical numbers here, we're looking for x-intercepts. For the y-intercept, we basically take our equation and we set the equation equal to 0. And when we try to do that or plug in, sorry, what am I saying? For the x-intercepts, we set the equation equal to 0. For the y-intercept, everywhere you see x into the equation, you are going to substitute x is equal to 0, and that will give you the y-intercept of 0, 0. Okay. So we have to keep all of these steps straight, and as you can see what I just did, it's very easy to mix up your steps. Now for step 3, it says we have to determine the critical numbers by setting the first derivative equal to 0. So I have my equation. I just have to apply the power rule in order to get my first derivative. Now remember, we finished module 2. So in our lessons, I'm not going to be spending time on calculating the derivatives anymore. And we are going to assume that you're very comfortable now applying the derivative rules to get the equation of the derivative. Now 3, 12, and 9 all have the greatest common factor of 3 in common. So I can factor out the 3, and that leaves me with a quadratic equation that is very easy to factor. So now, because I am solving for critical numbers, not X-intercepts, I have the X values for my critical numbers. X is equal to -3 and X is equal to -1. But I have to plug these back into the original function to find f of -3 and f of -1 in order to get my critical points. So plugging in those two X values will give me Y values of 0 and -4 respectively. So you have to remember to plug it back into the original equation, not the first derivative, in order to get your critical points. As you can see, I'm just summarizing what you have already learned. Step number 4 reads, determine the possible points of inflection. And we have learned that in order to determine the possible points of inflection, I have to use my second derivative equation. So by taking that quadratic function and applying the power rule, I get a linear function, 6x plus 12. If I set 6x plus 12 equal to 0 and factor the greatest common factor of 6, that gives me a possible inflection point of -2. But it's not enough to just have the X value of the coordinate. I need to plug in X is equal to -2 into my original function to find the Y value of a possible inflection point, which gives me the point -2, -2. So to summarize, I have one possible inflection point and two critical numbers when X is equal to -3 and X is equal to -1. So steps 5, 6, and 7 relate to the first derivative test and the second derivative test to figure out local extrema as well as points of inflection. Now, previously we did this with separate charts. Today, I'm going to do it with all in one chart, all one sign chart. So over here, I have my two critical X values, my critical points, and -2 belongs to my possible point of inflection. That gives me a test value between the interval of -∞ and -3, a test value in between -3 and -2, a test value between -2 and -1, and a test value between -1 and +∞. Now, it doesn't really matter what test number you plug in those intervals, but no matter what you choose, your first derivative is going to yield these signs, and the second derivative yields these signs. Now, it's important not to mix up the two. So, for example, the positive first derivative sign indicates an increasing interval between -∞ and -3. The negative first derivative sign it pertains to a decreasing interval between -3 and -2, and so on and so forth. Now, for the second derivative, if I have these two negative values indicate that between -∞ and -2, my graph will be concave down, and in between -2 and +∞, the graph will be concave up, even though we move from increasing to decreasing and then decreasing to increasing. If I sketch this out, not with exact intervals, remember these intervals are not spaced out, well, in this case they might be, but often they're not spaced out exactly, but this is what it translates to: concave down and increasing, concave down and decreasing, concave up and decreasing, concave up and increasing. So you will note that at -3, we in fact move from an increasing to decreasing interval. So that is a local max. Because we move from concave down to concave up at -2, that is in fact a point of inflection. And then moving from a decreasing interval to an increasing interval does end up, or it does result in a local minimum. So the sign chart confirms what our algebra revealed to us. And if I actually plot this on Desmos, I will have a graph where I have a local max at -3, a local min at -1, and a point of inflection at x is equal to -2, as well as 2 x-intercepts. So all of the information fits what we found on our time chart, when it comes to increasing and decreasing intervals, concave down versus concave up. So when you're doing your unit guides, really pay attention to the graphs and not just the equations. Make sure that your equations make sense of the real graphs. Okay, so that's one straightforward example. Remember, this whole week, I'm going to be breaking up our day into small examples at a time to really go through them in detail. The next example involves a rational function. So we have x squared minus 3x minus 4 in the denominator. And whenever we're dealing with rational functions, we want to make sure to factor completely my rational functions. If I factor my denominator and set it equal to 0, I find that there are restrictions on the denominator. So x cannot be equal to -1, x cannot be equal to +4, which results in vertical asymptotes at x is equal to -1 and x is equal to +4. Now, because the degree in the denominator is higher than the degree in the numerator, we do have a horizontal asymptote at y is equal to 0. Remember, early on in curve sketching, you learned all of these rules about horizontal asymptotes that reinforced what you learned in the MCR course. Okay, step 2. So in this case, we had a step 1. There were restrictions to state. Step 2 is X-intercepts and Y-intercept. But because what would normally we would look at our X-intercepts and Y-intercept actually correspond with our asymptotes. There are no X-intercepts, and if you let y is equal to 0 and try to cross multiply, you will find that the X-intercepts just don't work out. With the Y-intercepts, I would just plug in 0 wherever you see x in the equation, and that does result in a number -1/4 or -0.25. So there is a Y-intercept for this function. Now, because this is a pretty straightforward quotient, we do have to apply the quotient rule, where the derivative of the numerator is 0. But because our denominator is quite complicated, we end up getting x squared minus 3x minus 4 squared. But the numerator is fairly simple to simplify. However, with the first derivative, when I try to, you'll notice that we have the same denominator as the original function. So the x-intercepts also, we have to verify that the restrictions, are going to be the same, because if I factor my denominator, I'm still going to have x is equal to 4 and x is equal to -1 that are not in the domain due to my restrictions, my asymptote. Therefore, they cannot be critical numbers. Okay, so setting that equal to 0, they cannot be critical numbers. However, if I set this derivative equal to 0, it eliminates my denominator, but I still have my numerator, which then I can set my numerator equal to 0 and solve for x. So there is an x value, and which results in one critical point. And that critical point will occur when x is equal to 1.5. Now, the second derivative, remember the first derivative is a very simple quotient, but because the denominator is to the power of 2, you will see that the steps for the second derivative can be quite complex. It results in taking the greatest common factor on the outside and the leftovers inside the square brackets. Remember, and where some of you lost marks on the test, is when you didn't show, you would list the step, but you wouldn't show the distribution and how we move from a more complicated step to the final answer. So just as I'm showing here, it's really important to apply the distributive property, collect like terms, so that when you get to your final simplified answer, your teacher should be able to look at all the steps that come before and really understand how you got to the answer. There shouldn't be a large jump. We shouldn't go from this step all the way to the answer. Okay, so if we set this equal to 0 again, you will find that I have the equation 6x squared minus 18x plus 26, because the denominator will be eliminated. Of course, the denominator results in the same asymptotes, which makes sense. The asymptotes carry on to the first derivative as well as the second derivative. However, with the second derivative, it points to the fact that there are no real solutions for 6x squared minus 18x plus 26. Therefore, that proves algebraically that the graph has no points of inflection. If you are unable to solve for x by setting the second derivative equal to 0, that clearly means that the graph has no points of inflection. We can verify this in a sign chart. Okay, so this actually takes me to the example that I want to do next time. Okay, so really clearly there are, because we do not have the critical numbers and we do not have the points of inflection, we are unable to go further for this particular question. But for our next lesson, we are going to explore a problem where we're going to have quite a complex sign chart. And I think that, sorry, what happened here is that the slides got a little bit mixed up. So let's ignore this slide for a second. We will move from solving that there are no points of inflection to actually creating a sign chart. Because we had one critical number, we didn't have any inflection points, but we did have critical numbers. And in the case when you don't have, where you do have vertical asymptotes, you do have to include those in your sign chart. So for example, I have a vertical asymptote at x is equal to -1. I have a vertical asymptote at x is equal to 4, and I have a critical number at x is equal to 1.5. So just with limits, I need to figure out what is the behavior of the graph to the left of the vertical asymptote, to the right of the vertical asymptote for each asymptote. So we start with -infinity, and we have this interval up till our vertical asymptote. Then we have the behavior of the graph in between the vertical asymptote and 1.5, which is our critical number, and the behavior of the graph from 1.5 to 4, and then the behavior of the graph again from 4 to positive infinity. That gives us 4 possible test values. And with the test values, we find that my graph is going to be increasing as well as concave up in between -infinity and the first vertical asymptote at x is equal to -1. Then we move from concave down to staying concave down, but an increasing interval that peaks at 1.5 and then a decreasing interval from 1.5 to 4. At this point, at the asymptote again, the graph moves to concave up and another decreasing interval. So what that looks like is, because of our horizontal asymptote, we have that changes, that explains why the graph goes from increasing concave down to decreasing concave down. And it also proves that we do have a local maximum at my critical number. So there's a local maximum at x is equal to 1.5, y is equal to negative 0.16. So no points of inflection, but there is a local maximum. And if we were to go ahead and graph this function, it would look something like this, with the horizontal asymptotes, 2 vertical asymptotes, and my local max. And the sign graph correctly predicts increasing intervals versus decreasing intervals, as well as concave up versus concave down. So in tomorrow's or our next lesson, we are going to also be incorporating the idea of how to factor polynomials that are larger than x to the power of 2. So x to the power of 3, x to the power of 4. So for those of you who would like to review MHF concepts, you would have to review synthetic division, or make sure you understand how to use synthetic division, because as we are factoring these large polynomials, we need to understand how to break it down into the primary factors.